Heat trembles the shallows as a shape liquefies into stone, then sand, then weed. Ridges rise like pixels, shadows tilt to meet the sun. A hunting glance scans past and continues, fooled by a surface that calculates before thought. This is not paint, and not a trick of air. It is skin, tuning itself to physics in real time, the cleanest kind of camouflage. Edges soften, a head becomes a rock, the rock becomes glare. For a heartbeat, the predator hesitates, and the body below seems to have vanished. Call it camouflage physics, skin that solves light, and the puzzle begins. Coastal shelves and seagrass meadows offer both shelter and exposure. Here, hard contrast rules: rippled sand, spotted algae, broken shell. A small, flexible predator patrols these mosaics, hunting crabs, prawns, and small fish, then vanishing when larger mouths arrive. Its survival depends on reading texture and luminance, on turning background into shelter faster than danger can close the gap. The behavior looks simple: a shift in tone, a flurry of texture, a stillness. Yet the engineering underneath runs deep. Pigment organs expand, structural reflectors reroute light, broadband scatterers smooth the result. In studies of animal behavior, this rapid blend ranks among the most elegant displays of adaptation in the sea. Only after following the coastline's broken light do we meet the name, the common cuttlefish, Sepia officinalis, spread across the North Atlantic and Mediterranean. Short-lived, highly visual, endlessly precise. Chromatophores pepper its skin, tiny elastic sacs of yellow, red, and brown pigments, each ringed with radial muscles wired to the brain. Beneath them, Iridophores create angle-dependent blues and greens. Leucophores provide white backscatter. Patterns assemble as if printed. Uniform, mottled, disruptive. Muscle fibers in hundreds of thousands of units can engage within tens to hundreds of milliseconds. Field and lab studies report pattern shifts well under half a second, often near the reflex times of a blink. And yet the ocean does not pause. Sun striations drift as waves move. Suspended sand grains twist the spectrum. Copying a background that won't hold still risks an energy budget that won't hold either. The paradox is blunt, and it sets the stakes for everything that follows. How can neural control and photonic skin microstructures match shifting backgrounds in milliseconds without consuming unsustainable energy? The question sounds simple until the numbers close in. A body of this size, with this many controllable elements, should pay a heavy metabolic price to track light, texture, and motion. Instead, evidence suggests the ledger often stays in the black. That mismatch, the apparent speed and thrift, keeps rewriting what we thought we knew about sensory motor limits in the sea. One possibility is distributed computation, with local rules layered over a global command. The optic lobes set a coarse target, uniform, mottles, or disruptive, based on features like spatial frequency and contrast at a viewing distance. Then local circuits and the biomechanics of each chromatophore field refined the edges. In this view, the skin is not a passive display, but a mesh of semi-autonomous modules. Trade-off: local decisions reduce bandwidth demands from brain to body, but they risk errors when the background changes at scales larger than a patch of skin. Studies indicate those errors are rare when predators view from typical distances, suggesting the system is tuned to what matters most. A second hypothesis invokes extraocular photoreception. Opsin-like proteins in skin would let patches sense brightness directly, nudging chromatophores without routing every update through the eyes. If true, the skin samples light where it must perform, trimming delays and neural traffic. The cost is specificity. Local brightness sensing may misread complex edges or color casts that the central visual system could interpret correctly. Scientists still debate how strong and how fast these skin sensors are in shaping final patterns. A third route leans on passive optics. Iridophores and Leucophores act as photonic filters and diffusers. Angle-dependent reflectors can shift hue as the sun moves. Broadband scatterers can average chromatic noise from the water column. In effect, a fraction of matching comes free, offloaded to materials that bend light with minimal energy. The trade-off lies in control. Passive structures are fast and cheap, but limited in palette and directionality. Yet, together with selective activation of chromatophores, they may supply the last few percent that make a body untraceable. In all three, adaptation is not a single lever, but a coalition of tuned parts, a pragmatic answer that fits the constraints of animal behavior in coastal light. This, at heart, is camouflage physics, skin that solves light. Energy economics close the loop. Muscle fibers expand pigment sacs, but elastic elements and clever duty cycles can hold a pattern with reduced cost once set. Rapid bursts to change state, then a glide. Studies indicate the major expense is the transition, not the hold. That division encourages decisiveness. Pick the right pattern class, commit quickly, and stop paying. Stand over the meadow, and the trick makes a final turn. The sand still ripples. Light still walks across the bottom. The cuttlefish does not chase every shimmer, it selects, and selection is the point. What it chooses to ignore is as important as what it renders. The body becomes an argument about perception, the predator's acuity, its viewing angle, its distance, its attention. From that vantage, the mimicry looks perfect because perfection is defined by the hunter's limits. The animal has not disappeared. It has been tuned to the eyes that matter, and for those eyes it has, for now, vanished. What remains is a quiet question with sharp edges. If a brain, a body, and a layer of engineered skin can solve sight this quickly, what other sensory shortcuts wait in plain view? Every time the background tilts and the pattern holds, the ledger balances again, and the mystery breathes. The ocean writes one set of equations in light. The skin writes another across muscle and microstructure. Between them sits a creature that makes a living by solving both. The case is open, and the scene is unchanged until the next glance arrives and finds nothing at all.